Now that we have built our first model with the weight field, we would now like to look at how good is this model? How do we evaluate it? What can we do to improve this? So the equation that currently stands is miles per gallon is equal to 37.285 minus 5.344 into weight of the car. Now, what I'm going to do now, introduce this below. I'm going to use the weight field from my original input data, what you see here, and run it through the equation. So when you run it through the equation, you will get miles per gallon for each of the car. In an ideal world, that value should match the original miles per gallon. We don't live in an ideal world, and any analytical model is an approximation logic. It's trying to approximate it. So it gets closer to these values, but not necessarily. So what we have to do is we have to generate a predicted miles per gallon using the equation and then compare it with the original miles per gallon field. In order to predict it, all I have to do is create a variable predicted miles per gallon equal to my model name dot predict, and I give my x. So x is the variable with which I built the model in the first place. I built it. It has given me an equation. Now I am reusing the same x to see how good is this equation. I run that. Now for each of my 32 cars, I have predicted miles per gallon. I already have my original miles per gallon sitting in the y field. So what do I make sense of? What do I do with this? So just for sake of comparison, I'm just going to create a new column in my original input file, or let's call this as predicted miles per gallon. There's nothing there. Let's do a in file dot head. As you can see, so you don't have to do this. I'm doing this just for the sake of explanation. For the first car, if I had used the equation with this weight field, the mileage that the model predicts is this. The reality is this one. So we are slightly off by about 2 miles per gallon. If you look at the second prediction, it's about 21.9, and the reality is 21. The third one is roughly about 24.88, and the reality is 22. So you can see that it is relatively closer to the answers. It's about 2 miles, 3 miles here and there, quite different from the actual value. Now, when you have thousands of these observations, we will not be able to compare every single observation. So we want to have some kind of a measure or metric that will help us to quantify these differences. So there is a calculation called root mean square error. The calculation is very simple. You subtract the miles per gallon and the predicted miles per gallon. You get some positive differences and you get some negative differences. You square them, so they all become positive. You add them all together and then you take an average of that. So I could just simply subtract 21 minus 23.28, the whole square, plus 21 minus 21.9, the whole square, plus, and so on. Add them all together and I can calculate an average. Now because I have squared it, once I've added, I can do something called as square root. So I don't have to do this manually. There is a function called root mean square. mean squared error, that is available as part of the metrics package. All you have to do is pass the two columns together. So the mean squared error requires the original target variable, which is your original miles per gallon, which is currently sitting in your y variable, and your predicted miles per. So when you run this, you get a value. Now this is a value that can be 8, can be 20, it can be 400, it could be 50,983 for all you care. It is the square of the differences added and then averaged out for all your observations. Now when you look at 8.69, you will not be in a position to interpret it as a good number or a bad number. It's pretty similar to a variance calculation. In fact, we compare this to the real variance calculation. Now, instead of mean squared error, there is an alternate way of looking at this metric called as the R square. The invocation is very simple. It's R2 score, and then you pass on the two values. R square gives a value of 0.75. Now, R square is a value that will always vary between 0 and 1, regardless of the data that you are working on, regardless of the use case that you are looking at, regardless of the metrics of measurement. R square will always vary between 0 to 1. Higher the value, better it is. So if you see an R square of greater than 0.5, it means that you have a very decent model. Now in our case, R square is a value at 0.75, which means with just one variable, the weight of the car, our equation is able to explain how miles per gallon is impacted. The variability in miles per gallon is explained really well by just the variance in the variability in your input data, which is just the weight of the car. Now, what is this intuition behind R square? In order to understand this, you need to understand something called as a baseline model. That's the other terminology we are introducing. What is a baseline model? A baseline model is also called as the worst case model. Now, what is it? Now, if you really look at it, the simplest way of coming out with a prediction for a regression kind of a problem is simply use the mean field. For instance, if I were to ask you, how long does it take from your office to your house? Within a second, you are going to give me an answer. Maybe it is 1 hour, maybe it is 45 minutes. How did you come out with that? Essentially, you would have gone to the same office from your same house for the past couple of years. So even if you did 230 trips, one-way trips per year, so 460 trips per year overall, mentally you have taken an arithmetic mean to come out with that. So if I ask you, if I tell you this, tomorrow there is a meeting at 8:30 in the morning, you will make up your mind to leave at maybe 7 or 6:30 in the morning, because you are using your past experience of 1 hour or 1 hour and 45 minutes, whatever it is taken, and then you are using that to predict what is going to happen tomorrow, and accordingly you are going to use it. So using an arithmetic mean is a very simple approach of applying predictive analytics. Now mean, using the mean to predict miles per gallon of a car. So regardless of what car I place in front of you, if you just use mean to predict the miles per gallon, It is an approach. So you may be right, you may be wrong. Why are you going to be right? Because of the law of central tendency. It says most of the observations tends to be around the mean. So if I give you 100 new cars, most of the cars tends to be around the average miles per gallon. So if you use miles per gallon as a predictive approach, you're not going to be way off. But we also call that as the baseline model or the worst case model. Can I improvise over the baseline model? Absolutely yes. Now R square is an indication of how good is the improvement over the baseline. In a very simple sense, I know the equation might be wrong, but if you look at R square, it is nothing but 1 minus variance calculated on your data with respect to the regression line, which is nothing but your mean squared error, divided by the variance with respect to the mean line. So if I were to do a quick calculation, the mean of the car or the miles per gallon is around 20.02. So if I subtract y minus 20.02, I have these answers. Now if I square it, I get these answers. If I do a mean of that, oops, if I sum it, and if I divide it by number of observations, I get something like this. So this is the variance calculation with respect to the mean line. So what I can do, if I subtract the root mean square error or mean square error divided by I get 0.75 with some approximation. So as you can see, the R square that I obtained here is pretty close to it. I did a little bit of approximation on the mean value, hence it's slightly off, but you can see this is how R square is calculated. So what you can see from the equation is that if I had just used the mean, my variability or my variance is 35, but if I use the regression line using weight as an input parameter, then I am getting only 1.867. So R square is an indication of what is an improvement over the baseline. And that makes this fantastic because R square is always ends up as a ratio. And you know that if this value with your regression line is, if it is a significant improvement over this, then essentially R square will go towards 1. At the worst case scenario, your regression line is not way off from just taking an average, then R square will tend towards 0. Now some data sets are pretty complicated. Now sometimes very difficult to get excellent input parameters. So your R square may not improve. You may get maybe 0.4 or 0.5. It doesn't mean that you have a very bad model. It's still an improvement over just guessing with the average score. So this is how you can interpret the output of your model and check if you can improve this any further. Now with just one variable, I have an R square of 0.75, which means that if I add more variables, I may be able to improve this further. Let's do that next.